movement, but there are three movements of the stapes. The second movement is that from one side, okay, it is going inside like this and coming out like this, inside, but it goes a little obliquely and one side goes more deep inside and it does not go straight. This kind of hinge, like opening the door, as if like this movement also. So the whole thing is moving plus a little hinge movement also. And the third movement which is happening is if high intensity sounds are coming, then this bone, okay, is doing the job, but it rotates a little like this. There is an annular ligament module which is holding it, sealing it, and it moves a little like this so that it does not go inside very deeply. It is again protection. So there are three possible movements. Number one, piston movement, the most important one. The second movement is a slight hinge-like movement, and the third is rotational movement, only a protective one in some cases, special cases only. Okay?
If it were a completely closed and inflexible system, the movement of the stapes would be unable to displace the parallel, and therefore unable to send vibrations into the bony structure. Due to the flexibility of a membrane called the round window, the stapes movement can displace the parallel, allowing vibrations to enter the labyrinth. The corridor leading to the round window is found within the spinal portion of the bony labyrinth, known as the cochlea. Vibrations produced by the stapes are drawn into the spiral system and return to meet the round window. The portion of the spinal passage in which vibrations ascend to the apex of the cochlea is called the scala vestibuli. The descending portion of the passage is called the scala tympani. A third structure, called the cochlear duct, is situated between the scala vestibuli and the scala tympani. The cochlear duct is filled with a fluid called endolymph, and when viewed in cross-section, the membranes separating the two fluid-filled systems are visible. They are Reissner's membrane and the basilar membrane. The membranes are flexible and move in response to the vibrations traveling up the scala vestibuli. The movements of the membranes then send vibrations back down to the scala tympani. A specialized structure called the organ of Corti is situated on the basilar membrane. As the basilar membrane vibrates, the organ of Corti is stimulated, which sends nerve impulses to the brain via the cochlear nerve. The actual nerve impulses are generated by specialized cells within the organ of Corti called hair cells. The hair cells are closely covered by a structure called the tectorial membrane. As the basilar membrane vibrates, the tiny clusters of hairs are bent against the tectorial membrane, triggering the hair cells to fire. The entire basilar membrane does not vibrate simultaneously. Instead, specific areas along the basilar membrane move variably in response to different frequencies of sound. Lower frequencies vibrate the basilar membrane closer to the apex of the cochlea, whereas higher frequencies produce vibrations closer to the base. This arrangement is known as tonotopic organization. Together, this sequence of events is responsible for our acoustic perception of the world around us.
So, you saw that video. That's amazing video, really, okay? And this is an award-winning. This gives you a concept really This is actually what is happening inside our ears, okay? How the system is designed and how we see what is happening. Especially the cochlea is a very complex structure to understand its orientation, okay? This video really facilitates. There is another one, which is there. I'd like you to see that video yourself at home. I'll leave it for you because it will be a repetition. It has some extra things also that will make your understanding perfectly clear about the whole structure of the ear and the transmission of sound. I'd like to finish the lecture with few notes really, and because some of the things are still there, few parts, we are almost done. Advantage of that plane which was going, okay, the Yara was going and I was trying to speak, okay. Well, that is a very high intensity sound. But imagine if you are in a place which is very noisy and everybody is humming and buzzing around you. For example, Bufia, you go to the Bufia, everyone is talking really, and you enter the Bufia with your friends, 2 or 3 friends, and you find a table and you sit on the table and you start talking. Surroundings are so noisy and heavy really that all those noise is going into your ears, yet you are sitting, I'm sitting with you 3 and this is the distance and I'm still talking. That sound is coming and we are still managing and listening to each other. This phenomenon is called the masking effect or the masking phenomenon, which happens in the middle ear cavity also. In a very noisy environment, there is some tightening of the tensor tympani muscle and to some extent stapedius, not like attenuation reflex, but there is some contraction, more tightening of the muscle. They hold the system a little more rigid. So that noise of high frequency which is coming, okay, that noise is masked. It is not finished, it is still coming, but that noise is a little less, and in that less background of noise you can still manage to talk and listen to each other. That is called the masking phenomenon. That is again by virtue of these 2 muscles which are there, tensor tympani and the stapedius muscle. So we talked about the different phenomena. We talked about the attenuation reflex, which is a protective reflex, and another adaptive phenomenon which is happening in the ear, which when we are talking, when we are at noisy places, we are going in a factory or we are on the road where the traffic is going, there is Zama and horns and sounds are there, and still we are talking to each other and still listening to each other. So this phenomenon is called the masking effect. Okay? But this is the fascination of the middle ear cavity. Are we clear about that? Okay. Now, we are done with that. We are done with the process. Okay. These are the centers, areas of the brain which you have already done previously in the CNS also. Nothing special about it. Yes, deafness, when there is a problem in hearing or impairment of the hearing or inability to hear something, has different types. Okay. One type is known as the what type of transmission of sound do we have when it is passing? What system is it? It's passing through the outer ear, then middle ear, and then inner ear. When it is passing through the outer ear, which medium is it passing through? When it is passing through the middle ear, which medium is there? Air again. It is passing through the ossicles, but around the ossicles there is a medium of air module. We know that, okay? But what about that one? Fluid. Air, fluid. Okay? It's air transmission, it's ossicular transmission, and it's fluid transmission. But air, and fluid. Do you agree with that? speaking, you are hearing. You are speaking, you are hearing your own sound, isn't it? Okay? When I'm speaking, what is the route of transmission of the sound? How is the sound going into your system? Simple. What we described right now, okay? Air and fluid system, khalas, isn't it? So this transmission it's a conduction. Air conduction is going on, isn't it? So my sound, any sound from outside, it's air conduction passing on. Okay? All of you. Knock the skull table, all of you, your skull. Something is happening? Do you hear anything? This tuck 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 is going inside? How? Is it passing through the air? Sure? Sure. What are you striking? Bone. The outer table of your skull, isn't it? Your skin and then your bone. And then passing through the skull table, then deep into the bone. Then you are entering into the petrous bone. And then you are entering into the inner ear. You are not going into the middle ear cavity. Why would you go to the middle ear cavity? There is no point. Okay? So, how is it going? Is it going through air? Then it is going through bone transmission. This is called bone conduction. This is air conduction, normal route, and this is bone conduction. When I am speaking, what conduction are you having? When you are speaking, what conduction are you having? Both. Air, definitely, but your system is vibrating from inside, like this, and through your own bones of your, it's going inside. Come on. Okay? So it's a two-way transmission which is going, isn't it? It's air conduction mainly, but also it is vibration, isn't it? Through your own system, it's going. You got the point? So now you can differentiate between the air conduction and the bone conduction. Okay? You will have certain tests, inshallah, in the skills there, and that will tell you about very interesting test about the air and bone conduction. Final note. Yeah. Yes, tuning fork test. You place it here. If you place the tuning fork here, are you talking about the bone conduction or air conduction? Bone. But if you are listening here, it is air conduction. You compare the air conduction and bone conduction. Which conduction would be faster and better, air or bone? Think and answer properly. You will feel this one sound better and quick, or you will feel this sound better in intensity and in transmission. Bone or air? Try it yourself. Okay? Which sound is more crisp? Yeah, well, this is not a good example. The example would be if you are using the same thing for both purposes. For example, tuning fork. If you vibrate and place it, you'll feel vibration. And when you for a long time, really, okay? It's a musical sound which is coming and it is being transmitted, right? So, and that's only vibration. There's a lot of difference between the quality. Air conduction is far superior than bone conduction. It does work, but not like the air conduction, no match. Air conduction is taweel. When you stop the bone conduction by tuning fork, and you bring the tuning fork here, after that, oh, it will take a long time really to disappear even after that. Okay, so it's more than 2 times as long as your bone conduction. Okay, you will prove it in your lab, skills lab, inshallah. Okay, you got the point? Okay, now deafness. There are 2 types of deafnesses, main categories. One is called the nerve deafness and one is called the conduction deafness. How would you differentiate very quickly? Okay, just imagine and answer me. Nerve deafness, what do you mean by nerve deafness? When nerve is damaged. That is it? Which nerve? Okay, so are you talking about the nerve or the pathway? Both. Okay, so it's nerve and pathway. Anything else?
The nucleus
Yes, when you say pathway, actually it covers everything, okay? From the receptor to Merkus, anything is damaged in between will give you nerve deafness, sensory neural deafness, or perceptive or the perception deafness. You cannot pick, you cannot receive the sound, Istiqbal is not maujood, the receptors are not there, or they are not working, or the transmission in the pathway is not there, or the Merkus is not working anywhere. It is about the sensory neural loss or the deafness, okay? Is that reversible or irreversible? Most likely it is irreversible. Neuronal damage, come on, okay? Conduction deafness, where are you now? Conduction deafness, what are you talking about? Before the receptor, yani? Either in the middle ear or in the external ear. Any problem here, blocking like this, if you just close. Now can you hear the same thing in 2 ears from your mouth? Okay, your transmission is decreased. It's a temporary deafness which you have developed. Okay, you leave it again. All right. Any blockade, tumor, foreign body, wax, infection, swelling, edema, any problem inside, if there is closing, it is conduction problem, conductive deafness will be there. Tympanic membrane, damage, infection, inflammation. Okay. Ossicles, they are damaged. Middle ear cavity infection, any problem, any fluid accumulation, any blood, any pus, anything, any disturbance, disease. Again, you stick in tube block, it's all about the conduction deafness. Yani, external and middle ear cavity, if you have a problem, what kind of deafness the person will have? And if there is a problem from the internal ear, beginning from the internal ear, right up to the level of the pathway, if there is a problem, then it is the sensory neural or the perception. Yeah?
There is a problem in the inner ear. It is not conduction deafness.
Inner ear where? What are you like?
The bone, like the cochlear bone is broken or something.
Cochlear bone, okay, now that's a good question. If the bone is broken, then cochlear bone breaking is affecting the function of the receptors. If it is affecting the function of receptors, that their sensitivity changes or they are not able to receive it, even though the bone is broken inside the ear, it is not the direct effect of the receptors. And indirectly, what are affected? Receptors, neurons. If they are affected, where will you place it? So generally speaking, internal ear problems will not be considered as conductive. Once you are into the inner ear, any problem in the fluid system, any problem in the neurons, any problem receptor, fibers, pathway, you will take it as the sensory neural problem. Okay? You will classify. Both conductions can both? Yes, definitely. Okay? So one is reversible, usually conduction, other is not. Okay? And we have the tests to differentiate between the conductive and the perceptive deafness. These are the tests you are going to perform in the skills lab. So I am holding myself. Have you done it before in the skills lab or no? You have not. So you will have, I think, next week, do you have any skill lab or no? Okay. If it is there, you will have the tuning fork test, which are perfect tests, really very interesting. We'll talk more about that. Any problem, any question so far in the discussion? Is that clear? The video is yours. Please, the other one. Both videos, keep it, watch it when you are studying. Okay, that will improve your concept. All right. It is on the desktop.